we're going to talk about NP-complete problems and reductions. I'm going to do from scratch, assuming you don't remember anything from yesterday, and get everybody up to speed, and then actually get into the details of talking about specific reductions today and how they work. So here we go. Review. You are. P, that stands for a whole class of problems. Problems that you can make algorithms to solve them in polynomial time. There's lots of examples in here. A universe of problems. Hundreds and thousands of problems that can be done in polynomial time. And outside of this class, the next level of the bullseye are problems that can be solved in non-deterministic polynomial time. Okay, that's that magic machine that does things very, very fast in parallel when you allow it to do ORs connected together. I want to talk about a different way of thinking of non-deterministic polynomial time algorithms, a way that's easier to think of from an algorithmic point of view, and it's this. If you want to describe to me a non-deterministic polynomial time algorithm, do it in two stages. Your first stage is you get to guess a solution to the problem. You have to count how many steps it takes you to make that guess. That counts. But you get to guess it. You get that for free. And if you can check your guess and check whether it's right or wrong in polynomial time and make the guess in polynomial time, that's called a non-deterministic polynomial time algorithm. It's not realistic. In real life, you wouldn't just be able to make that guess and check it. You'd have to make all the guesses and check each one of them and see if any one of them worked out. This guess, or this guess, or this guess, or that guess. And you'd have to do them one after the other, and it would take exponential time, because there's usually an exponential number of guesses you'd have to try. But in a non-deterministic polynomial time machine, you get it for free. All those guesses get to be checked in some sense in parallel. So as long as you show me how to check one of them in polynomial time, you could check them all, and as long as one of them gives you an answer, you're all set. Okay? We're going to do examples of that in just a couple minutes. So there are problems that, as far as anybody knows, cannot be done in regular polynomial time, but can be done in non-deterministic polynomial time. It's like somebody gives you extra power, and now you can do more things. All right, questions so far? Right.
The word non-deterministic so bothers me. To me, that seems like something's happening at random, probabilistically. But that's not the sense here at all.
It is somewhat random. It's basically, if you think about the definition of it, really, at any point in the computation, your program has more than one choice. Think of it as you're going to guess one of the 2 to the n possible subsets. You can choose any one of them randomly, and then the program continues. The program is said to accept or say yes when any one of those ends up saying yes. So it's just a weird way of describing how a program says yes and how it runs. But there is a randomness to it. You can pick any one of them. It's just that we essentially only count it if one of them works out. If you pick the wrong one, that doesn't hurt. As long as there is a right one to pick, it's okay. So there is a randomness. What there isn't is this notion of the computation occurring stage by stage. I don't know if that was helpful, but maybe a little bit. When we talk about this in theory of computation, you'll understand exactly that here every choice is determined, and here you can choose at some point randomly. From the point of view of algorithms, just think of it, you're making a guess, you're checking your guess. That'll do for now, and it's essentially equivalent. So it's okay. All right, let's do an example of an algorithm that runs in NP, that's non-deterministic polynomial. Let's do it for the Hamiltonian circuit problem. I'll remind you briefly, this problem is the problem where you're given an undirected graph, or a directed graph, it doesn't really matter. You're trying to start at one node, go through all the nodes exactly once, and get back to where you started. Can it be done or can't it be done? Yes or no? How do you solve this in a non-deterministic polynomial time algorithm? Well, let's say I have 7 nodes, A, B, C, D, E, F, and G. Okay, the graph's over there. I won't draw it now, because if I draw it, you'll be more inclined to pick a certain order than another order. So it's behind the blackboard there. You have to figure out whether there is a Hamiltonian circuit in this graph. Say the only thing you know how to do is brute force. So we're going to guess an answer. We're going to come up with an ordering of these vertices. Say B, D, E, F, G, C, A, and then B again. I'm guessing that this is the answer to the problem. Okay? How long does it take me to guess? It takes me n steps to guess. Now I'm going to go do the second part of my algorithm. I'm going to check that this is really the right answer. How do I do that? I go to my graph, and I check if there's an edge from B to D. I just look it up. I go to the B adjacency array, I look for a D. And then I look and see if there's an edge D to E. And then I look and see if there's an edge E to F. And I go all the way through until I get to see if there's an edge A to B. And if the problem checks, then I say yes, there's a solution to the Hamiltonian circuit problem. The answer is yes. And if I go through all these things and one of the edges doesn't exist, I say no, the answer's not there. So as long as I can make the right guess and check it in polynomial time, then I have a solution for this problem. And if you're thinking, well, that's not realistic, you're right. In a deterministic version of this, I wouldn't just be able to guess one and check it. I'd have to try them all to make sure I got the right answer. And I'd say yes only if one of them, if the first or the second or the third or the fourth or the last one ended up being yes. So the deterministic version of this algorithm is much longer. The non-deterministic version is just do one of them. The deterministic version is try all of them. All right. A little abstract. Are there questions about that? So how long does it take to do it? It takes order n time to make the guess, and it takes order e time to check all the edges. Or order n time, depending on how you implement it. So it's linear time, non-deterministic. All the power is in the non-determinism. How long would it take me if I did it deterministically? It would take the same n time for checking, but I'd have to do that checking for each of the possible permutations of these nodes. And there's a lot. How many are there? This is one of them, but I started with 7 nodes. If I want to order them any way I like, it's going to be n factorial. So the deterministic version would be linear times n factorial. And that's hideously exponential. Right? Really, really bad. By the way, that's the best anybody knows for this problem, is to do that exponential algorithm. So we don't know anything better, because this problem really is NP complete. OK, let's do another NP algorithm. This problem is called the Clique problem. In the Clique problem, you're given a graph. Here's an example. You're also given a number, because this is a maximum problem. So you're given a number, say like k, an integer. And you're asked, in this graph, can you find k or more nodes, all of which connect one to the other? A clique is sometimes called a complete graph. It's like a group of people who hang out together. So a triangle is a clique of 3. A clique of 4 looks like this. And a clique of 5 looks like this. The problem is to find the biggest clique in this graph. Okay? And maximum problems turned into decision problems are given a graph and a number k. Can you get a clique of k or better? K or more? What's the answer in this question, by the way?
3.
For sure 3. Can you get 4? I don't know. I just made it up. Maybe you can get 4, maybe you can't. This problem is hard. It's hard to get the maximum clique. If I fixed k, it wouldn't be so hard. If I said, does it have a triangle or does it not have a triangle, you could answer that. In fact, in general, if I fix k, you can solve this problem in n to the k, because you can just look at all the subsets of k nodes. And there's only n choose k of those. Yeah?
I think I get that. Is it, I mean, you have to turn, like you have to specify a k to make it a decision problem, right?
Right.
So if in specifying a k, you make it an easier, a significantly easier problem, which seems to be the case sometimes.
If the k is fixed to a constant, like 3 or 4, then the problem is an n cubed or n to the 4th algorithm. But if I ask for the maximum clique, then k can go all the way up to n.
But that's not a yes or no question.
Yeah, I'm asking, does it have a clique of 3 or more? Okay. Yes or no?
That's the, okay. So I get it.
And in this case, I'm asking, does it have a clique of k or more, which means that k could go all the way up to n. That would be an n to the n algorithm, and that would be really slow.
So you specify, so for yes or no questions, we're using this numerical boundary.
Yes,
thing.
yes.
You specify a minimum or a maximum.
You specify the thing you're trying to beat, right. And that thing's a variable, so it can change.
Still infinite possible. Okay.
Right, right. So in this case, the maximum version is hard, but if I fixed it to a specific version, the problem's polynomial time. But let's not talk about the deterministic version. Let's talk about the non-deterministic version. How do you solve this non-deterministically in polynomial time? What do? You're trying to find a clique of k or more. Well, yeah, so what if you do that? So there's 4. Well, you're given k. K is given to you.
So
Right.
count the number of edges out of a node, it should equal k, otherwise you could just discard that node. If you want to find a clique of k, right?
Yeah. Right, so if this, you can discard that node, but you might go through all of them, not discard any, and still not know if there's a clique.
Check,
You need to do something after that.
check every combination of k nodes and see if they connect.
Okay, so that's a follow-up. Once you check that you can't rule anything out, you have to look from all the combinations of k possible nodes. But then what? How long does that take? Nobody's using non-determinism to help. We still need to cut this down with our.
No,
Just
it
pick
would
k
take,
nodes. And see
since
if
you've
they-
We'll
already
just
got
guess
them
the k
selected,
node.
you just check to find out whether they connect.
Okay, good.
Then-
Good. So instead of checking every possible collection of k nodes, there'd be a lot. We're just going to pick k nodes. We're just going to guess k nodes. That's our non-deterministic guessing set. That's what we get by magic. We guess k nodes, and then we just have to check whether every single pair of nodes in that set of k is going to have an edge between them. How long does that take? How many pairs of nodes are there in a set of k? K squared, right. So it takes k squared steps to check a guess. It takes k steps to make the guess. K squared plus k is polynomial. And that's all you have to do to solve the problem in non-deterministic time. You make a guess and you check the guess. Yeah, Joe, 1 second.
So if you guess, and you guess, let's say you're looking for a 4 in that
Okay, so let's say k is 4.
right?
So now we're going to pick
And
a...
you guess wrong.
Yeah, good. So let's take these 4. And now I start checking them. And there's an edge, an edge, an edge, an edge, but there's no edge between here and here. And so therefore I don't say yes.
Even though there might be one in there, you just return a no.
No, we don't return anything. Non-deterministic machines don't return anything. As long as one of their guesses has a way of saying yes, that's what it returns. So all the wrong guesses don't count against you. As long as there's one guess that works, we say it solves the problem. It better not say yes if there's no guesses that work. If they're all wrong, it better never say yes. But as long as there's one way that'll work, you assume it finds that way. So this guess is always, imagine that it's lucky. Mike, you had a question?
How does this, so we were looking for 4 better. So do we then do this also simultaneously with k is 5 and k?
No, because you just pick 4, and if you win, you're all right. I mean, if there's one with 5, then there's be one with 4. If you find one with 4, the answer is yes.
Oh, because the 4 pieces would connect.
Right,
Okay.
right. You didn't have to go for 5 or 6 or 7. You just go for 4. So when they give you the k, you just pick k and you just do that. You don't have to go to the next cases.
Say what? Why?
Michael was...
Just because of this non-deterministic.
No, because the problem's asking, is there a clique of size 4 or bigger? So if I find one with 4, I'm done.
If you actually think of it as the machine, so it's guessing all these things in parallel and checking them, right?
Fine.
I mean, it could, if you're thinking of it that way, it could fail to find one at 4 and find one in the category.
No,
That's just...
That would be a problem. You're right, Chris. That would be a problem. It would be a problem if it failed to find one for 4, but then might have been successful for 5, 6, or 7. But that can't happen. If it doesn't find a clique of 4, it's never going to find a clique of 5. If there's no group of 4 people, all of whom like each other, then you're not going to find a group of 5 people, all of whom like each other, because every subset of 4 here likes each other.
Yeah,
so we just have to pick the lowest one. Yeah, it's okay. But it's an important point to mention that you don't have to go past the highest one that we're looking for. Checking that 4 is fine. All right, let's do another one.
Where are we going with this?
Nowhere.
What's the next step? So I can appreciate this step. It seems really odd right now.
Yeah, it should seem odd. Here's how you should feel now. You should feel like, all right, I can do almost everything with a non-deterministic machine. It's so darn powerful. What's the point of inventing something that's not realistic and is so darn powerful? It's specifically to show that some things are hard to do. If I give you this machine, you can do all sorts of stuff. Stuff that you can't figure out how to do deterministically in a fast way. And I'm going to prove to you that if this problem in particular, and a lot of other problems in particular, if they could actually be figured out how to be done in polynomial time, then all these other really hard problems that you can only do with this powerful machine, they could also be done in polynomial time. And nobody expects that to happen. There's 500 problems that the smartest people in the world have all thought about. Nobody's figured out a way to get them inside this bullseye. And if you could figure out a way to get clique inside this bullseye, then you figured out the solutions to all the other problems. So we invent this very, very powerful thing to kind of point out just how hard these problems are. That the only way we seem to be able to get them is with this very powerful thing, and we probably couldn't get them if we took the power away.
A complete graph.
Yes.
K. It also includes a k-node complete graph. Then how is it different from the specific k case where you just say, is there or is there not one for 4? How is 4 or greater different from 4?
It's not. If I always ask 4 or greater, then I can do it in n to the 4th.
Or 6, and if you ask, is there one of 6 or more,
then I can do n to the 6th. Right. That's true.
You're saying that was an easier problem, complexity-wise.
If I always ask, does a particular graph have 6 or more, then I can do it in polynomial time. I can do it in n to the 6th. But the thing is that we really want to find the biggest one. Not whether it has 6 or more or 7 or more. We want to find the very biggest one. So when I would normally call clique to find the biggest one, I wouldn't put in 4 or 6. I would put in n.
But once you convert it to a decision problem, you're no longer looking for the biggest one. You're looking for, is there one of this or more?
Right.
Which is equivalent to, is there one of this size, right? Exactly?
Right. So how would I use that decision problem to mimic my maximum problem? If I want to find the biggest one, and all I have is a decision problem, I said you can always use decision problems to do these maximums. So how would I simulate the maximum problem using the decision problem? I wouldn't ask for 2 or 3 or 4 or 6. If you give me a 100-node graph, I ask, can you find out a clique of size 100? If you tell me no, I'll ask, can you find a clique of size 99? If you tell me no, I'll say, can you find a clique of size 98?
Okay. So
those algorithms are not polynomial time because the exponents that I'm calling them on are proportional to n. So they're n to the n and n to the n minus 1, and I have to add them all up, and I get an exponential time.
Okay.
Does that make sense? So
yeah, I guess.
I don't want you to get too hung up, because this is really a technicality that can hang you up, this distinction between when you try to make minimum and maximums turn into decision problems.
Yeah,
and it's not the main idea. It should bother you a little, because it is a technicality that we have to fudge a little. But, you know, I can stick to just yes-no questions and stay away from these max-min, but not like this one. 3D matching. This This is the last NP algorithm we'll talk about, because they're all kind of the same, and like Neil says, it seems confusing, and I think we need to ground ourselves back and talk about more specific, concrete things. But the last example, 3D matching. By the way, there are notes about these problems at the very beginning of class, so you don't have to copy these down. I mean, you can look at the first 2 days' worth of notes. 3D matching is this problem. It's the Mars problem, right? The 3-gender problem. You have 3 genders on your planet. X, omega, and... and what? I see. Yes, from someone who would know. X, omega, and Joe. 3 genders on Mars. On Mars, people get together in triples. You're either this gender, or this gender, and you can only union and have a house full of kids if you get together 3 people. So, we have a bunch of people, 100 of these, and 100 of these, and 100 of these. Okay, equal. So we conceivably could match everybody up if there weren't any objections. So everybody on this planet is polled, and somebody comes up with a long list of triples that everybody agrees are okay. You know, so let's call these x1, x2, all the way to x100. So maybe x30, omega 45, and Joe 15 is a reasonable triple. These 3 people are willing to live with one another. You got yourself into it. You picked it. Now there's 100 Joes. This list can go very long. We have a long list of triples that can live with one another. And the question is, can I match these all up without violating any of the conditions? Yes or no? Everyone understand the question? The 2-dimensional version of this is polynomial time. Okay, it's called maximum matching. It's related to the maximum flow problem. It's a well-understood problem, and you can do it in n cubed. When you stick it up to 3 dimensions, goodbye. All bets are off. It's much harder.
What is like the list bit? Like, doesn't it depend on how long that list is? I mean, there's always...
The size of the input is the length of this list plus the number of different people in the genders. So if you want to call the length of that list m and call the length of this n, okay, then nobody's got a way to do it short of exponential related to those 2 parameters. Okay. So this list can go as long as you want.
There's a way to find out from that list whether
right.
or not I get it.
Right. Well, I mean, what's the limit to this list? If I have n values, what's the most you can have here?
3.
What is it? We got 3 positions. Each of them can have n things in them. So what is it? N to the 3rd or 3 to the n? Big difference. 3 to the n? N to the 3rd? Dimitri, you tell us. You know. N cubed, right. You can put n different things there, and for each one of them, you can have a pair of these. How many pairs of these are there? You can put n things here, and for each one of them, you can have n matches. So there's n squared of these, and I can match those n squareds with every one of these n, so it gives n cubed altogether. Okay? So it is n cubed. That means the worst I'm ever going to have, Chris, is that the list here will be n cubed long. So if I can do it in polynomial time in n, I can do it in polynomial time in terms of this list. Everything's related polynomially. Okay? So here's a yes-no question. How do you solve it in non-deterministic polynomial time? You're going to guess the answer. How do you guess the answer? You need to come up with 100 triples. So you guess 100 triples. That takes 3 times 100 steps. Okay? You take your guess, and for every triple you have, you go through this list, and you look to see if it's there. And it better be there. And if it's there, you say, okay, I go on. So for every one of your triples, every one of your 100 triples, your n triples, you go through this list, which can be at most n cubed. So it takes n times n cubed to check the answer. So it's non-deterministic, and it's polynomial time.
Is this a pretty easy reduction to the disjunctive normal form, whatever it was. The first NP.
Oh, where does it?
Just
Oh, it's not such an easy reduction, but
it looks so similar.
it looks similar? Good. You got good instincts.
Well, I doubt it is. I'm just curious. If
No, you're right. It is similar.
well, they're all similar. That's cheating.
Hey, how come we just can't? How come we just can't do this deterministically in polynomial time? You should always ask yourself that question. What did you gain by having the non-determinism? What we gained is we could just guess 100 triples and check them. We could check them fast. But how long would it take us to actually try all these guesses? How many guesses are there for these 100 triples? Well, there's n cubed different triples, right? There's n cubed different triples, but now we're taking a collection of 100 of them. Every one of the 100,
N cubed, choose 100.
Yeah.
so it's big. It's like n cubed to the 100, more or less. So that puts this parameter here in the exponent and makes it exponential. So trying all the possible collections of 100 triples is an exponential process. Checking one of them is a polynomial process. So as usual, non-determinism cuts out a big exponential factor. Let me give you one important fact. I won't prove it, but it's very intuitive. If you give me a non-deterministic algorithm, and I want to actually do it deterministically, no matter what your non-deterministic algorithm is, I can take every choice you ever make and just try it. I mean, the worst you're going to have is lots and lots of choices. There's got to be a polynomial number of choices. I can try all of them, one after the other, and I will always be able to figure out the answer deterministically as long as you give me exponential time. So I'm going to put a big bullseye around non-deterministic polynomial and write exponential time. So here's polynomial time, non-deterministic polynomial time, back to regular deterministic, but now I'm exponential time. So it's sandwiched in between. Any non-deterministic polynomial time can be simulated by a deterministic exponential time. It's a lot to pay. Okay, you want this powerful object? Pay me with exponential time. You got to say, hey, the price is too high. Okay. Questions about this 3D matching? I think now we're ready to talk about reductions, and now it's where things will get more concrete. Okay. All right. In this class NP, there are some problems that are harder than others, or at least as hard as all the others. I put little stars in them. They're the ones that are called NP-complete problems. They're the ones that if you could solve them in polynomial time, if you could figure out a way to get them inside here, then the two bullseye rings would collapse and be identical. Then all the other stars outside in this constellation would really be inside. And in that sense, these starred problems are as hard or harder than all the other problems in NP. How do you prove that a problem is as hard or more difficult than all the other problems in the class? Well, it's a real tall order. And I mentioned last time it was a tedious, detailed proof done simultaneously by Cook and Levin in different places, different problems. And they each took an arbitrary algorithm, anything you come up with, and showed how to convert it to a particular problem. And that's what a reduction is. The best way to describe a reduction is by giving an example outside the context of NP-complete and then working our way back here. And it's a reduction that we've done before. Before we did a reduction, that shows that sorting reduces to the convex hull problem. What did that mean? Intuitively, this symbol means sorting reduces to. We read reduces to convex hull. Intuitively, it means convex hull is going to be harder than sorting, or at least as hard. And the way we did this problem, the way you do any reduction, is you take the input to the problem on the left. You fiddle with it, and you make an input to the problem on the right. All right? Take the input to the problem on the left, fiddle with it, make a new input to the problem on the right. Mathematically, we call that a function. We say If x is an example of the sorting problem, then do f of x and turn it into an input to the convex hull problem. You change it. And there has to be this particular property that has to hold. The new input for the convex hull problem should say yes, or be solvable, if and only if the original input to the sorting problem is solvable. That the solution of one relates to the solution to the other. In this example, it's really straightforward. Let me give you the way we do it. Somebody gives you a bunch of numbers. 8, 3, 15. You want to sort these numbers. Here's the reduction. Here's how to turn it into a convex hull problem. Here's my reduction. 864, 39, 15, 225. I give you these points. The reduction is to take the numbers, which are the input to sorting, and turn them into points, which are the input to convex hull. You're taking instances of one problem, turning them into instances of the other problem. And what has to be true is that whatever this tells you about convex hull should tell you something equivalent about sorting. If you come up with a convex hull of these points and get them in order, it will be the same order as these points, because they end up lying on a parabola. That's the intuition behind reductions. In this problem, this is not decision problems. There's no yeses and nos here. So it's going to be a little different from what we do. What we do will be easier. We're going to want this instance to have the answer yes whenever this instance has the answer yes. We want this instance to have the answer no whenever this instance has the answer no. So that way, if I want to solve this problem using this problem, I can run it through the reduction, solve this problem, and whatever this problem says, that's the answer to the original problem on the first instance. Okay, that's the important idea, so I'm going to say it again. If you have a reduction from this problem to this problem, from sorting to convex hull, then I can sort numbers by doing convex hull. I can use the problem on the right to solve the problem on the left. And the way to do it is first run through your reduction, converting the instance here to an instance in the second problem. Solve the second problem, because presumably you know how. Get an answer. Whatever your answer is will be the answer to this instance on the original problem. It's just changing your domain. How long does it take you to find a convex hull? It takes n log n. How long does it take you to do this reduction? N. So I can do sorting in n log n by using convex hull. You're thinking, well, I know how to do sorting in n log n without convex hull. And you'd be right. It's okay. This is not the best way to do sorting, perhaps. But at least it's one way. Yeah?
In our algorithm, the first thing you do in convex hull is sort.
Yeah, that's true. Well, and one of them we did. One of them we didn't sort. One of them we did.
So this would be used to prove something about convex hull, not about sorting, right?
You can use reduction to prove things on either side, depending on what you do. I'm going to show you that today. So you can do both ways. But I want to mention one thing. Let's just say that this reduction, instead of being linear, was n squared.
It's not a reduction.
Well, it's a reduction, but it won't help us much, right? Because convex hull solves a problem in n log n. I can still solve sorting by going through this reduction, but how long will it take me? The worst case is the reduction part. You want the reduction part to be the easy part. You don't want the reduction part to be giving you the weak link in your chain. If I do this, if I say, okay, I can solve sorting by doing a convex hull problem, you want the convex hull problem to be the complexity of your algorithm. You don't want the reduction to take all the work. So when we do reductions, we're going to try to make them as simple and as fast as possible. In this case, it's a real competition between how long it takes convex hull and how long the reduction takes. In our examples, we're going to be doing reductions between problems that are NP complete. So they're all really hard. So the only thing we're going to require about the reduction time is that they're polynomial, is that they're less than exponential. This one is actually a linear time reduction. But all the reductions we're going to use are polynomial time reductions. And we could write it like this. I'm going to leave out the word poly because every one we're going to use is going to be polynomial. But really, you should assume that there's a word polynomial here, which means the reduction didn't take me a long time. Beginners often make reductions that are exponential, which are not really useful reductions at all.
Are there many useful reductions where the reduction is more complex than what we're reducing to?
No, if the reduction is more complex than what we're reducing to, then the reduction is kind of useless. Yeah.
Suppose if there was no sorting algorithm in existence, it would still be useful, right? Or if the
Sure.
high exponential sorting algorithm or something.
Right, if you thought sorting was very hard, then you've basically done all the work in the reduction step, right? Okay, let me get a little more specific. Let's do a real reduction. What's a good one? Let's do this. I need to tell you what these problems are, and then we need to do the reduction. SAT stands for Satisfiability. That was the first problem proved NP-complete by this guy, Stephen Cook. It's the one where he took any algorithm you want in the whole world and turned it into an example of satisfiability. Satisfiability problems look like this. You have a formula, a Boolean formula in conjunctive normal form. There's ands in between each row. There's ors in between the variables. And you want to know, can you make an assignment true, false that makes all these things end up being true? That makes the whole formula work out to be true. Okay?
There's absolutely no limit on how many can be in each.
No limit on how much can be in each clause. No limit on the length. Okay. How would you solve this non-deterministically? Pick trues or falses for each one of the variables, and then go through the clauses one by one and check to see if they're true. How would you do it deterministically? You'd have to try all the possible true and falses, and there's 2 to the n of those. So deterministically, it takes exponential time. Non-deterministically, you can do it in polynomial time. It's a hard problem. It's NP-complete. What I want to show you is that even if I restricted these problems to examples where there were exactly 3 variables in each clause, not 1, not 2, not 5, not 8, but just 3 in each one, the problem is still very hard. The problem is still NP-complete. Okay? If you knock it down to 2 in each clause, then the problem can be done in polynomial time. So that's exactly the frontier. If I keep it 3 exactly, it's still hard. If I make it down to 2, the problem's easy. We're going to talk about both those directions. Here's the first one. The way I'm going to show you that the 3 version is hard is I'm going to show you that if I could solve the 3 version, then I could solve any version. Everybody get that? I'm going to reduce the general version to the 3 version. Yeah, Donna.
By 3, do you mean 3 different variables? Or you could have any number of variables, but only 3 per clause?
Any number of variables altogether, but only 3 in every clause. Okay. Yes.
And what's the variable that we're figuring the complexity on again? You told us before, but is it the number of sets, or is it the number of variables?
Let the number of variables be n, and the number of sets be m. Then it's any combination of these. So there's 2 parameters in the size here.
So where neither of those are in the exponent.
Right. Okay. Neither of those can be in the exponent. Right. All right. So we're going to do a reduction. We need to take a general example of the satisfiability problem and turn it into an instance of the 3 satisfiability problem. We need to think, how are we going to take a list of things that look like this and turn them into a list that have exactly 3 in each one, where the answer to the 3 example will be the same as the answer to my original example. Okay? This is a medium difficult reduction. It's kind of a local replacement. We're going to be able to work with the reduction in a local way. Sometimes reductions are a big, big global kind of a picture, and it's components, and it's tricky. And here, it's kind of right in the middle. We can pick it out in pieces, and you'll see this in a second. There's also reductions that are completely trivial, but this is not. This is kind of in between. All right, so I need a method that's going to take a general formula and turn it into a formula with 3 in it, such that the true or falseness of the 3 formula will be identical to the true or falseness of this one. When this one can be true, the original can be true. And when the original can be true, then this one can be true. It's got to be related if and only if. This way, if I succeed in doing this, then if you want to solve this kind of problem, you bring it to me, I run it through my reduction, I come up with a set of 3, I hand it over to somebody who knows how to solve this, they give me a yes or no answer, and I send that yes or no answer back to you. That means if this could be done fast, then your problem can be done fast, as long as my reduction doesn't take too long. So I'm going to make sure my reduction takes polynomial time, so that if this one is in polynomial time, then so is this one. And by the way, Cook showed that every single problem in NP reduces to satisfiability. That's that first amazing theorem. Every single thing, the whole class of NP reduces here. So if I could show you that this one is in polynomial time, it would imply this one is. And if this one's in polynomial time, it implies everything in NP is in polynomial time. And that's just not believable. All right. So let's get rid of that part. Let's work on this. Let's do this locally. Let's try to convert this formula into one with 3 in each one, where the true and falseness stay the same, but we don't have to worry too much about how each conversion of a clause is going to affect conversions of the other clauses. We can just work locally. So let's start with the x. And we'll do this in general, but let's work on an example first. How do I take that x and turn it into something with 3 in it that's the exact same as this? Yeah, you're supposed to have different ones, but I guess we could. X or y or not y, is that the same as x? X or y or not y is going to be true. We want it to be the same as x. How about this? X or, well, let's not use y because we're using it here. Let's use auxiliary variables. X or a or b. X, a, b bar. X, a bar b. X, a bar b bar. Look at this collection of 4 things. If this collection is true, then how do you know that x has to be true? Because I have all the combinations of a's and b's here, so one of these 4 is going to be 2 falses, no matter what you do for a and b. And whichever one that is, the x in that one has to be true. So if you can make these 4 true, then x is going to be true. And if his x is true, then definitely these 4 can be made true. So it's back and forth. These 4 are equivalent to this. You can prove with a logic table that these 4 are equivalent to this. You never wanted to do that again the rest of your lives, but if you had to, you can make a big logic table. X, true, false, X, A, B, all the 8 possibilities. Make the columns, check that this and this are equivalent. So, general speaking now, anytime you have a single variable, turn it into this, where the A's and B's appear nowhere else except here. These are my own little private A's and B's.
Do you have to do that? I mean, you should be able to use any variables.
Well, as long as they don't match up with these Y's.
Well, why? Why would that be a problem?
Well, maybe you're right. Still, I just like it because it's clean. Maybe you're right. Maybe I could borrow them. But I like to think of them as auxiliary, and I want them to be clean. Maybe you're right, Chris. Maybe that's a good point. Certainly, it's OK to have them be separate. Doesn't hurt. All right, what's another? Yeah, Todd? Yeah. Chris? Yeah. Let's continue. So now I know how to take care of single variables, turn them into stuff with 3. All right, how do I take care of things like these? Yeah, good. So I got these and these. How do I take care of things with doubles in them? Good. But not A bar and A, unless we, yeah, use C. Again, putting both these in makes the combination equivalent to just having these two, because one of them has to have the third variable be false. And that means the leftover is going to be exactly the same as x plus z bar. So I can take care of 2's, I can take care of 1's. How do I take care of the long ones? How do I take care of the long ones? Is that going to be a hassle? Are we going to get stuck, or are we going to be able to do it? We're going to be able to do it. How do I do it? Break it up into pieces. How do we do that? We need little ways to link them together. You got to be a little bit good memory on the old logic stuff. Let's break this into pieces. Y, x bar, I'll call it L for link. If this is true, how do I know that I can make both of these true? If this is true, then one of these four things is going to be true. One or more. Okay? Let's say it's y that's true. Then this guy's already all set. But then I have flexibility to make the L bar true. So I can make this one set. Right? As long as one of these is true, I can make this thing true.
So you're making the L or L bar be whatever you want it to be.
Right, because I can, because I picked it. Because it's not one of the other variables. It's just my own. I'm trying to show you that if this one line is true, then these two can be true. And if these two can be true, then that one line is true. So let's go the other way. Let's say all of these were false. That means this is false, this is false, this is false, this is false. Now whatever I do with L, I'm dead. Because one of these is going to be false, which means if all of these is false, one of these two has to be false, which means my whole formula ends up not working out. So these two are equivalent to this one. You might remember, this requires a little bit of memory because it's 3 months ago. Remember when you take two things like this and add them together, you can kind of cancel an L and an L bar? That's called resolution. So these two cancel and end up the same as that. That's appealing to memory. The first was appealing to logic. What if it was longer than 4? X, Y bar, W bar, Z bar, U, V. What if it was much longer? Can we still do it? How do we do it? X, Y bar plus link. I'll call it L1. What's the next one? Link 1 bar plus W bar plus the next link. Good. So when you have longer ones, you have to have just every new clause containing the next variable with links connecting the next ones. Then you get L2 bar plus Z bar plus L3. And then L3 bar. Now I think we can just add the rest in. Plus UV. So this turns into this.
This is why we can't reduce it to 2 set, because otherwise there's no room for actual variable.
Right. Right. It's hard to imagine how we could do this with 2 variables in every clause, because this linking specifically needs 2 for the linking and then 1 to get the next one in. And if we tried to do this with only 2 in every clause, we wouldn't have room for this guy in between. We just get lots of links with nothing to pass on. So it seems like we should expect to have trouble turning this into a 2-set reduction. And we do. We can't do it with 2. But before we get into that, it's a very good point. Before we get into it, let's go back and review. You give me a general instance. If there's a single one in, I'll show you how to convert it. If there's a double, I'll show you how to convert it. If there's long ones, I'll show you how to convert them. Since this is conjunctive normal form, every one of these is equivalent logically, and every one of these is equivalent logically to its collection. The ands of all these will be equivalent logically to the ands of all these. All these will be able to be true anded all together only if all of their equivalent things anded all together will be able to be true. So I make my conversion, I check whether this is true, and that tells me whether this one's true. Now, how long did it take me to do this conversion? How hard is this reduction to do? Every single variable thing takes 4 steps. Every double variable thing takes 2 steps. Every long one takes how many steps?
Minus
some proportion to the length of this. Okay? So what's the most steps altogether? If every one of these had all the variables in it, then the worst that could possibly happen is m clauses, n variables in each one would be n times m. That's the worst this would take me. So it's definitely a polynomial time reduction. I'm not doing anything exponential here. I do a polynomial time reduction, I get the components done, and I'm ready to go, and I can solve this general problem with this specific problem. Let me stop for questions. Jeff, okay? You get it? Who's got a question? Yes.
Is there something fundamental about this problem that makes it the root of NP-complete, or can you pick other points and also make them the root?
Any point could have been the root. This is a very natural description of a language, Boolean formulas, you know, true and false. In fact, what we're going to do right now is going to leverage exactly that point. And we'll get to it in a second. But certainly, any of the NP-complete languages could have been the first one. This just happened to be the first one.
Just set the direction of the inequality between the two. It's just that one has more variables. The three set. If you get them equivalent now, you can reduce what you can transfer.
Yes, that's true. They're now equivalent because 3-sat is an NP, and we know that it could definitely reduce back. In fact, the reduction back is completely trivial. The reduction back is don't do anything to it. I mean, everything in 3-sat is also in sat. So that's one of these trivial reductions. There's just nothing to be done. If you can solve satisfiability, you can certainly solve 3-sat. Just give me the instance. I won't touch it. I'll just run it through. So they definitely go in both ways. Once you take an NP-complete problem and reduce it to another problem in NP, then they are essentially equal. Because everything reduces back to NP. And 3-sat is an NP. So if that's what you're asking, the answer is yes. All the NP-complete problems are equal one to another, equally hard. And at least as hard as all the other problems in NP. All right, questions? Yeah, Ty.
You've increased the number of variables and the number of clauses, but just by a polynomial?
Exactly. We've increased the number of variables and the number of clauses, but just by a polynomial. And if we had increased it by an exponential factor, this would be trouble. Why would it be trouble if we increased it by an exponential factor? What would we have done? You think you can solve sat by doing 3-sat, but if the reduction does exponential work, then you can't solve it in polynomial time using 3-sat. You'd have to take your instance to sat, do exponential work to do the reduction, then solve it using 3-sat, but your whole process would take exponential time, and that's not helping me at all to solve satisfiability. So you got to keep the reduction smaller than the things you're trying to compare. If you're working with NP-complete algorithms, the reductions have to be polynomial. If you're working with n log n algorithms, the reduction should be linear time or better. Yeah.
Seems we've talked about, you know, if we are actually solving these problems deterministically, sometimes some problems are 2 to the n, some problems are
n factorial, right?
So those are all very different orders of growth, even though they're all exponential. So how does that relate to reducing one to the other?
Well, these reductions are all, if you could make one polynomial time, then the other one would be polynomial time. And the fact is that none of them are.
Right.
And some of them are worse than others. So there's really no relationship. The reductions do not address the fact that some of these problems seem harder than others as far as the order of complexity. That some might be n factorial and some might be 2 to the n. But if you could solve one in polynomial time, the other still would be. So it doesn't really address the fact of distinguishing between those. There are other complexity classes that attempt to distinguish between things that have different orders of growth within exponential. And that's in a different area. We usually don't do that in algorithms. We do it in a course called computational complexity, hierarchies of problems. Okay. I keep saying that everything in NP can reduce to satisfiability. And that you do this with one general reduction. It's just this really, really, tedious, hard reduction. I want to convince you that at least we could do this for one example. And it's going to be kind of easy. It's kind of easy to imagine converting any problem you want into Boolean formulas. And I'm just going to pick an example. not quite at random, but one that I think is not trivial, but also not horribly difficult. And I want to show you how to convert it into a Boolean formula. Okay? And that won't prove that everything in NP can convert to a Boolean formula, but it'll at least prove that that one example is and give you a sense of what it's all about. So now we're going to do this reduction. We're going to do 3 colorability reduces to satisfiability. Polynomial time. 3 colorability is the problem where I give you a graph and I ask you, can it be colored with 3 colors or less? Yes or no? Can you color it with 3 colors or less? Yes or no? I'm going to show you how to take this problem and convert it to a Boolean formula. If the Boolean formula can be made true, then the answer to the 3-color problem will be yes. And if the Boolean formula can't be made true, then the answer to the 3-color problem will be no. Everyone understand what I'm going to try to do? That way, if you could solve Boolean formulas, you could solve 3-color problems. Now, I know that there's got to be a way to do this, because I know I can solve this problem in NP, and I know everything in NP reduces to satisfiability. So this is a very special case of Cook's theorem. It's one of the infinite cases. Any algorithm at all in NP reduces to satisfiability. So certainly this one should. Let's figure out how to do it specifically. And you're going to help me this time. Here's a graph. A, B, C, D. I'm going to turn it into a formula. I want the formula to be true if and only if this graph can be 3-colored. Let's represent what it means to color this 3-color graph with a Boolean formula. Describe what has to be true in this problem to me. Describe it in English. We'll turn it to Boolean. Yeah, Joe.
What do you color? The nodes or the space?
You color the nodes. You color the nodes, and you try to make any 2 nodes that are adjacent not have the same color. So the first thing that has to be true, how many colors can you use for A?
3.
Well, 1 of 3 different colors. 1 of 3 different colors. How do we represent that fact? How do we represent the fact that A can either be colored red, blue, or green? I'll let AR is a variable that means if it's true, it's colored red. If it's false, it's not colored red. Okay? AB will be, sorry, let's make it red, green, and yellow. AR is colored red. AY would mean A is colored yellow. A green would mean A is colored green. How do I represent the fact that A has to be colored either red or yellow or green? Not any 2, not any 3, but 1 of those exactly. AR and not a green and not a yellow. Or good. A green and not a yellow and not AR. Or a yellow, not AR, not a green. These 3 combined guarantee that A can only be colored red, green, or yellow. And it has to be colored 1 of those. If these 3 are going to be true, then either AR or AG or AY has to be true, and no 2 can be true. Agreed? It's just we took the English and we turned it into Boolean. You do this for every one, for B, C, and D. I'm not going to write them all up. But you'd have to do it for every single one. So,
with the things you already decided taken into account, like at this point B and C could not, or do they all start?
Well, what we've done so far is just set up the conditions that every node has to have 1 of 3 different colors. We haven't put anything in about this graph. In fact, there's nothing in there that models the edges yet. Now we have to model the edges. And once we do that, then this is going to be able to be true exactly when this can be colored, and this will be false when this can't be colored. It'll be a 1-to-1. How do we model the edges? The fact that A and B are connected, what does that mean in English? Forget Boolean for a second, just in English. They can't have the same color. Now how do we convert that to Boolean? They can't have the same color. That means
A red implies either B green or B yellow.
Okay. So tell me how to write it. A red implies is that it? Well, let's just do the AB edge. You're right, Michael. I got to do more than this, right?
Yeah, it's also.
And it's also A green implies not B green, and A yellow implies not B yellow. Okay. That's fine for the AB edge. Now I got to do it for the AC edge. Is this enough? Is this enough for the AB edge? This says if that is A is yellow, B can't be yellow.
Actually, it has to be the opposite. It has to be equivalence.
Right. What if B is yellow? Then according to these rules, it's perfectly fine for A to be yellow. So you have to reverse them too. If BY is true, then AY is not true. BG, not AG. BR, not AR. These 6 represent this edge. We have to do those 6 for all the other edges, including the one AC that Mike just started to do, including the CD, including the BC, and including the BD. So let's count how big our formula just got. For every one of the n nodes, we have 3 clauses. For every one of the edges, we have 6. So it's polynomial. 3 times n plus 6 times e. Big formula. What's weird about this formula as far as our satisfiability problem goes? Right? It's not in this form that we assume it's in, which is conjunctive normal form. So now I am not going to do the details. I'm going to plead reference to discrete math. You can all take this big ugly thing and twist it into conjunctive normal form. And if you can't actually do it, you can at least remember that it can be done. All right? And it's important because that's just why you do discrete math. So at this point, I don't have to go through some horrible details convincing you of that. You could use your logic to turn this into formulas like this, and just your knowledge that every Boolean formula can be converted to the special form that we expect SAT to be in. So this can be turned into conjunctive normal form, and that would represent this problem precisely. Now, this reduction should have seemed easier than the other one, in some sense. I think it is. This reduction is pure. Tell yourself what this means in English and write it in Boolean variables. You can get good at this stuff if you do enough of them. And after you do about 50 of them, then you think you're doing really good, and then you realize that Cook proved that it's true for an infinite number of these. So when you do 50 more, you're just as close to getting his theorem finished. He proved it's true for everything. This just confirms that proof for one case. So keep in mind what he did was a very big deal. And it really works in general, and it's nice.
This is all ended together, right?
Yes. This and absolutely. Yes. Good point, Chris. Yes. One more thing, then we will quit for today. We're going to be doing reductions for at least 2 more lectures. And they will vary in difficulty from something more or less like these to much easier to much harder. And hopefully you'll see a great variety and then have some chance to try some yourself. And sometimes they're going to just work out for you, and sometimes it's going to take some hints, which I will be happy to give you. It's tricky at first. What I want to do today is, instead of finishing off with a reduction that's a negative result, one more thing that's hard for us to do, let's do a reduction that actually gives us a good result. When we start with a problem like SAT, and I reduce it to 3 SAT, what does that tell me? What have I really shown? If I already knew SAT is hard, which I did, I knew this was NP complete, then reducing it to 3 SAT tells me that 3 SAT is also hard, 3 SAT is also NP complete. If I can solve 3 SAT, I can solve this. If I could solve this, I could solve everything. Therefore, if I can solve 3 SAT, I can solve everything. Therefore, 3 SAT's NP complete. Everything would reduce to 3 SAT. This relationship is a transitive one. Everything reduces to 3 SAT if everything reduces to SAT, and SAT reduces to 3 SAT. All right, that's a negative result. 3 sets hard. What if I did a result like this? What if I knew that something's really easy, like 2 colorability? 2 colorability is really an easy problem. It's the same as checking whether a graph is a bipartite graph. You can do this with breadth first search. Take any node, all the nodes next to it have to be the other color, all the nodes next to them have to be the other color. If you ever get a contradiction, stop and say no. If you never get a contradiction, say yes. It's an easy problem. I could easily do 2 colorability goes to satisfiability. How would I do that? The same way I just did the other one. What I did for 3 colorability wasn't so special. I do the same darn thing. What does that tell me about 2 colorability? Does it tell me anything? It tells me that it's easier than satisfiability. Satisfiability is out here in NP land, and 3 colorability is in here. Sorry, 2 colorability is in here in P. It tells me what I know. It tells me that if I could solve satisfiability, I could also solve a problem that I know I can already solve very, very, very fast. So if I could solve a really hard problem, I could solve this really easy problem. No surprise. This kind of reduction is completely useless. You never reduce an easy problem to a hard problem. And you would expect a reduction like this to be easy to do, since you're going in a nice, easy direction. But it doesn't help you at all. You reduce a problem that you think is hard to another problem that you don't know about, and that shows that problem's hard. That's one way to use a reduction. Here's another useful way to use a reduction. We don't know about 2 satisfiability. We don't know whether we can get satisfiability reduced to 2 satisfiability. Chris said it seems like we're going to have trouble modifying this reduction we just did because we don't have that linking structure. Otherwise we'd be fine, but that linking structure is killing us. So I wonder if there's a way to take 2 satisfiability and reduce it to something else that we know is easy. What if I could reduce this to something like depth first search or something like shortest path? Then if I could solve those problems, which I know how to do, I'd be able to solve 2 satisfiability, and that would convince me completely that 2 satisfiability has a polynomial time algorithm, that it's really here. Here's 3 sat, but here's 2 sat. There's the frontier. There's no 2.5 sat, so that's just the best you can do.
Not only does it show that you can have an algorithm, it actually gives you one.
It actually gives you one. You do the reduction, and then you solve this problem. And then you can solve 2 sat. So I'm going to show you today a reduction between 2 sat and another problem. I'm going to show it to you. The problem is one you've seen before called strongly connected components. Here's what I'm going to do. I'm going to show you that if you want to figure out how to solve 2 sat, convert your instance to a graph, find its strongly connected components, and that'll help you know whether this is satisfiable or not. Okay. As usual, I'll describe the reduction by an example. And here it is. Here's a 2 sat example. X plus u plus y, x bar plus y bar. Somehow I want to represent what this is asking in terms of a graph. The same way I represented what a graph question like 3 colorability was asking in terms of English and then Boolean variables, I just want to change the language. Here's a question in terms of Boolean variables. Can you rephrase the question in terms of a graph? Reductions are rephrasings. People who are really good at them are just seeing the same thing through another language filter. That's all they are. They're changing the vocabulary of the problem to another domain. That's what we're doing here. Give me a Boolean formula. I'm going to show you how to convert it to a graph. And the question on the graph is going to be the same as the question on this Boolean formula. Well, how do we do it? Here's the idea. What does it mean to have this be satisfiable? It means that one or more of the variables in each clause have to be true. Why is this easier than the 3-sat question? Let me give you an idea. If I picked x to be false, what do you know? U has to be true. That's the one good thing about a 2-satisfiability problem. Once you know something's false, the other one's guaranteed to give you one. And then you can propagate that. If U is true, then all the U bars have to be false. So I go through all the U bars and take their pairs and make them true. And then all their bars have to become false, and I propagate that. And when I'm all done, either I get a contradiction, or there's some slack left, and I can make those variables anything I want. More or less, that's how you do it, but it's a little vague. I'm going to show you specifically how to convert this to a graph problem. Here's what we're going to do. We're going to look at the variables here. We have x, u, and y. For every variable, we're going to make 2 nodes. One represents x, one represents x bar, y bar, and u bar. We're going to make arrows between these nodes to represent what I just told you about false and true. In particular, if x is going to be true, if x is going to be false, then what has to be?
U has to be.
Then u has to be true, and then u bar has to be false. So if x is going to be false, what else has to be false? U bar has to be false. Everybody get that? I'm going to write that in. X being false means u bar has to be false. This edge represents that if this is false, then that's false. Agreed? It comes from this clause. Let's do the opposite way. Is that what you're thinking, Doug? Maybe?
Yeah.
What if u is false? Then x bar has to be, then x has to be true, x bar has to be false. So I have to make an edge from u to, did I do it right? Yeah, x bar. Everybody with me so far? I'm making arrows between variables where if I make this false, it means this has to be false.
We get crossbars automatically.
What do you mean by crossbars?
If x is true, then not x is, oh. Yeah, then not x is false.
If x is true, then not x is false, but that wouldn't be an arrow. We're making arrows between things. If this is false, then this is false. Right. So what else do we get? Let's do the rest of this. Let's represent this whole information with this picture. If y is true, if y is false, then u bar must be true, so u must be false. So we make a connection from y to, and then I have to make a connection from u bar to y bar. This is very mechanical. Look at the pair, start with one node, and make an arrow to the opposite of the other node. So x bar goes to y, and y bar goes to x. Oh, jeez. Great, up till there. There we go. OK, here's a picture that represents these dependencies in 2-sat. When are you going to be able to set these values to true and false? You can make anything you want. If I make this true, that means this. If I make this false, that means this has to be false, this has to be false. That's OK. Now I can pick this to be false, 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 false. It's OK. Let's see what happens. X is false, u bar is false, y bar is false. X is false, u bar is false, y bar is false. Right? And if you look at it, that's a perfectly fine, satisfiable assignment. There's no contradiction, there's no problem. Well, so what? How do I look at this graph and answer the question whether this can be done or whether it can't be done? It looks like I can always do it. When are we ever going to get a problem? In this case, I can do it, so you don't see any problem. So it seems like I could have just made any graph. Maybe we could always do 2-sat.
If an x and an x bar could be connected.
Let's add this. Now we can't do this two-satisfiable assignment. Now there won't be any way to do it. But let's see what happens in our picture. We need an edge from y bar to x bar, and we need an edge from x to y. What happens now when you try to set any of these variables to false? Pick any one you want and set it to false. It doesn't matter. Let's try this one. We'll set u to false. That means x bar has got to be false. That means y's got to be false. U's got to be false. Any problem? Let's write it down. Okay, so far, let's write it down. We started with u is false, and x bar is false, and y is false. So far, so good. Let's get the rest of the variables. Or let's check the rest of the clauses. Do I have this right? Yeah. Okay.
But if you started x,
No, I want to, this is already bad, but I want to,
start at x, you're going to loop through x being false, y being false, u being false, x bar being false, and x bar cannot both be false simultaneously.
right. If x bar is false, then x has to be true. So let's see what happens. Let's try to make this true. Oh, that's not going to be a problem. And maybe it's possible to do this. Does this just work? That I just...
Because y becomes true, doesn't it? If x is true, then y
X and y is false.
If you start on x, you're saying that x would be false, right?
If you made x false, you'd go here, 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 and you get a contradiction. So x can't be false.
Well, no, x also goes down to the y,
Yeah,
and then to the u.
yeah.
So we've said x is false, y is false, u is false. U goes to x bar, which would
Yeah,
say that x bar
right,
is
but-
false, and that's where we get our...
Right, so x can't be false. You can't make x false.
Right.
Because then we get a contradiction. So x has to be true. And we've made x true. And I think it should be okay then. So x can be true. U can be false. That makes that one okay. Y is false. That makes this one true. And x is true. So this is fine. There's no contradiction. Okay? But it almost got us messed up, because if you try to make x false, we'd mess up, right? So we had to be really careful here and make sure x was true. When would we really get stuck? I got one more to add. What if I add this guy in? That means y goes to x. I think this is good. X bar goes to y. X bar goes to y bar. Now let's try to make it through here and be successful. What's going to happen? I think now we can't.
For the previous four, x has to be true and y has to be false.
Right, this has to be true. If this is false, then we get a contradiction, because x bar has to be false. You can't have x and x bar both being false. That's the key thing. So if this is false, that's a problem. So let's make this one false. Is it all right?
No, it goes to y.
This is false,
But so is y.
and then so is that false. If we made this one false, it comes to here, and then to here, and then this one has to be false. Whatever you try now for x or x bar, whether you make one of them false or the other one false, it implies that its opposite has to also be false, which is impossible. Right. So one more minute, now we'll finish this example. I took this collection of two sat things. I turned it into a graph. I want to convince you that I can do something on this graph to tell you whether this is satisfiable or not. And here's what I'm going to do. You give me the graph, and I'm going to find its strongly connected components. I'm going to find in this graph all the nodes that can connect one to another. All the nodes that are in a linked collection of false variables. And I'm going to collapse them down into single nodes. So in this case, in the original case, u, x bar, and y would have been collapsed into one. That would have been one strongly connected component. If one of those is false, they all have to be false, like an equivalence class. I'm done doing that now. How do I figure out whether the answer to this is true or false? I look in each of the collapsed nodes, in each strongly connected component, and I ask myself, do any of them contain a variable and its complement? If they do, the answer to this is no. And if they don't, if all the complements and variables are in different strongly connected components, then the answer to this is yes, I can do it. So I took the logic and I turned it into a graph problem that relates to linking things together. It's really the same kind of a thing, but this makes it a little more visual. This is a hard reduction. It's tricky, it's complicated, but it shows that 2-sat can be done as long as you can do this. How long does it take to find strongly connected components? You can do that with depth first search, and it takes order E. All you got to do after that is look through each one for the variables, so it takes another n. So this whole 2-sat problem can be done in basically n squared time, in linear time. N squared for the variables, linear for these edges. All right, let me leave that there. We got a lot more reductions to do. You'll get a lot more experience. Look this over, think about this reduction. It's kind of a cool reduction, and we'll continue doing regular complete reductions next time.